From our last video, we have our model of energy levels and the idea that the transitions between the energy levels are associated with specific energy jumps and therefore specific colours of photons giving rise to those interactions. We want to now add some maths into this, so we want to give some values to those energy levels. Back to basics, because this adds another complexity. We have hydrogen here with its energy levels and an electron in the ground state. Let's do something new and ionize it. Let's provide enough energy to remove the electron from the atom. Just enough energy to bring it here. How much energy does the electron have now? We could measure it and find that we needed to provide 13.6 electron volts of energy, which is 2 times 10 to the minus 22 joules. Over here we have a mercury atom and it has 1 electron in the ground state as well. Notice though that the pattern of energy levels is different here. Also, we need to provide 10.4 electron volts to remove the electron from the atom. So, we now have 2 electrons that have been freed from their atoms. How much energy do they have? Think of it another way. Can you tell any difference between them? Can you tell which one came from hydrogen and which one came from helium? Or from mercury rather. Assuming we provided just enough energy to free them, the answer is no. The 2 electrons are exactly the same. So we now have 2 electrons that have been freed from their atoms. How much energy do they have? Well, we need a baseline really, and the easiest baseline is 0. So we say that at ionization, which is where both of these electrons are, at ionization the electron has 0 energy. I'll label that here, 0 electron volts. I already said the electron in the hydrogen atom needed 13.6 electron volts given to it, so an electron started here at the ionization level and then released 13.6 electron volts to get to the ground state, n equals 1. Then it must have 0 minus 13.6 equals minus 13.6 electron volts at the ground state. Each of these will have an energy associated with it too. In this case, minus 3.4 electron volts, minus 1.51 electron volts, minus 0.85 electron volts, and minus 0.54 electron volts. There are others I didn't draw. For the mercury, n equals 1 is minus 10.4, then minus 5.7, minus 5.5, minus 5.0, and minus 3.7 electron volts. So, let's get back to the question of colours. For the hydrogen, let's imagine an electron relaxes from n equals 2 to n equals 1. The change in energy, delta E, is equal to E1 minus E2, so minus 13.5 minus 3.41 equals minus 10.2 electron volts. So 10.2 electron volts is released. Okay, hang on, what's an EV? This is covered in electric fields, but quickly, the work done accelerating a charge of 1 coulomb through a potential difference of 1 volt is equal to 1 joule. That's going to be our definition. 1 joule equals 1 coulomb times 1 volt. If the charge is minus 1.6 times 10 to the minus 19 coulombs, then the work done is 1.6 times 10 to the minus 19 joules. Since 1.6 times 10 to the minus 19 coulombs is more simply written as E, then 1.6 times 10 to the minus 19 joules equals EV. And that's the definition of an electron volt. It's a small unit of energy for a small world. Right, so 10.2 electron volts is released, which we can now convert to joules by multiplying by 1.6 times 10 to the minus 19, giving us 1.6 times 10 to the minus 18 joules. We already know that E equals hf, and h, the Planck constant, is 6.63 times 10 to the minus 34 joules seconds. So F equals E over h equals 1.6 times 10 to the minus 18 over 6.63 times 10 to the minus 34 equals 2.4 times 10 to the 15 hertz. Using C equals F lambda, so lambda equals C over F, lambda equals 3 times 10 to the 8 over 2.4 times 10 to the 15 equals 125 nanometers. So ultraviolet or beyond. That was a pretty big energy though, so let's try our luck with n equals 3 to n equals 2. The same calculation gives me delta E equals E2 minus E3 equals minus 3.4 minus 1.5, which is minus 1.9 electron volts. Multiply that by 1.6 times 10 to the minus 19 and we get 3 times 10 to the minus 19 joules. Pop that into E equals hf, and F equals 4.6 times 10 to the 15 hertz. So lambda equals 650 nanometers. Red light. And that's the essence of energy levels and spectra. We have atoms that have specific energy levels and they've got a specific energy value associated with them. So the interactions can only have certain discrete values as we're moving from one energy level to another energy level. That means that the photons that interact can only have specific energies, meaning that they have specific frequencies and they have specific wavelengths, therefore specific colors.